All right, so last time we started talking about induction, and we did one example. I want to do everything today. We're going to do will just be examples, okay? So we're just going to do several problems. So we did one in which we actually verify a formula for adding consecutive integers, okay? The sum from 1 all the way up to n equals n times n plus 1 over 2. That's a very classical example. Now let's try this one. So let's see, a find formula. This time I'm not giving you the formula. This time we need to find it. And then we need to verify that indeed the formula works. That's what we're going to do, okay? So find a formula for the sum of the first n positive odd integers. Then prove it by using induction, okay? So understand that this is the first positive odd integers, okay? So we are only interested in the odd cases. So let's see. Typically, when you don't have anything, right, here we don't have any formula, what you should do is start doing some experiments and see if you can guess what the formula should be. Then you go ahead and you try to verify that this formula indeed works, okay? So let's see. N is the number of odd integers that we're going to be adding, right? So let's start by saying n equals 1. So what's the first odd integer? 1. So we have 1, and well, 1 is equal to 1, but there's nothing to do here. Yes? Now, when n is equal to 2, what does that mean? According to our statement, the sum of the first two positive odd integers. What are the first two odd integers? 1 and 3. So we're talking about 1 plus 3. Yes? So what's 1 plus 3? 4. Okay? We'll go for more. N equals 3. Who can tell me what does this mean? Read the sentence now with n equals 3. What does it say? Read the sentence with n equals 3. What does it say?
So it's 3 plus 5.
Read the sentence with n equals 3. I said it 4 times. Can you just read the sentence and replace n by 3?
Find a formula for the sum of the first 3 positive odd integers.
Good. So, what are the first 3 positive odd integers? 1, 3, and 5. In other words, we need to find 1 plus 3 plus 5. Do you understand this? Okay. What is this?
Okay.
9. Okay. Let's do one more. So when n is equal to 4, what is this?
1 plus 3 plus 5 plus 7.
1 plus 3 plus 5 plus 7. That's the sum of the first 4 odd positive integers. And what is this? 16. Okay, so maybe here we can stop. Do you notice something? Do you notice any pattern?
Yeah.
So if you have to make a guess, what do you think will be the result when n is 5? What do you think should be when n is equal to 5?
25.
Good. So we're expecting to get 25. In other words, if I do 1 plus 3 plus 5 plus 7 plus 9, I get 25. So what's happening?
Taking a perfect square.
Say that again.
N is a perfect square.
So we are taking a perfect, so we are obtaining perfect squares, right? So if I now add up the sum of the first n numbers, if I do 1 plus 3, let's say when n, in the n situation, if I keep on going this way, so 1 plus 3 plus 5 plus 7 all the way up to, and now in this case I have to do 2n plus 1, right? So notice that, let's see, if I do 1, that's 3, that's too much, so I'm gonna do 2n minus 1. So notice that when n is equal to 1, this sum right here stops at 1, because this means start at 1 and finish at this value, okay? So when n is equal to 1, this value is 1, so I start at 1 and I finish at 1, yes? When n is equal to 2, this is 3, start at 1, finish at 3. Do you understand this? When n is 3, this is a 5, so I finish here, and so on, okay? So when you get to the nth, the sum of the first n odd positive integers can be expressed like this. You have to put 2n minus 1. You put 2n plus 1, you're putting 1 more. You have n plus 1. You don't have n integers. Okay? So is important. So according to the pattern, what should this be equal to? This is, remember, these are the first, this is the sum of the first n integers, n odd integers. What should this be equal to according to the pattern? N squared, very good. So notice that here, this was 1 squared and n is 1. Here, this was 2 squared, n is 2. 3 squared, n is 3. 4 squared, n is 4. 5 squared, n is 5. So it looks like when you add the first n odd positive integers, you get n squared. So if you add the first 1,000 odd positive integers, the result will be 1,000 squared. 1 million. You understand this? 1 plus 3 plus 5 plus 7, all the way up to, so let's see, the first 1,000 odd positive integers, that will be all the way up to 1,999, right? Because this is 2,000 minus 1, 1,999. If you add all of those odd integers, you're going to get 1 million. Okay? That's what we're claiming. And in fact, we're claiming that this is going to work no matter what. Okay? So this is our conjecture. This is the formula that we are coming up with. Now, our job is to verify that this always works. We only verify up to 5. How do we know that if we go all the way up to 1 million, it's going to work? How do we know if you keep on going, this is going to work always? Okay, so we need to convince ourselves. So, the formula, and I'm going to call it now conjecture, is that the sum of the first odd positive integer, of the first n odd positive integers is, so what is it? What's our conjecture? N squared. Okay? Which, if you want to write it in more mathematical terms, like using some algebraic notation, what we are saying is that 1 plus 3 plus 5 and so on, all the way up to 2n minus 1 is equal to n squared for all n greater than or equal to 1. Okay? That's what we're saying. Now, notice that everything that we're doing, you could start at 0 if you want. And many people like to talk about induction starting at 0. And if you do that, then you have to switch this to n plus 1. Because if your first index is 0, then you need to do plus 1, so your first number will be 1. Okay? And then that's fine. Okay. So, questions? Do you understand this formula? This is what we came up with just by doing some examples. Now, let's go ahead and let's prove it. Okay? This is a conjecture. Conjecture means something that you believe is true, but you're not sure. You don't know. You haven't proved it yet. Once we prove it, now it becomes a theory. Okay? There are many conjectures out there, some of which are worth $1 million. So you can try. There's a very simple one. It's called go-back conjecture, but nobody has been able to prove it yet. That basically says that every even number can be written as a sum of 2 primes. So if you can prove this, you can get $1 million in your pocket. Okay? So for example, 4 is 2 plus 2, and remember 1 is not prime. I don't know, let's say, 16, you can write 16 as 13 plus 3, both of which are prime, okay? And so on and so forth. It says every even number greater than or equal than 4 can be written as a sum of 2 prime. That's called go-back conjecture. And nobody has been able to prove it yet. We have checked it with computers up to whatever number, but computers you can only check up to a finite number because there's a limit to how big the numbers can get in a computer because of the architecture, right? So, it appears to be true because we haven't found a counterexample yet. But we cannot say it's true because we don't know. What if in the super millions over there, it's a number that's not going to happen? So still a conjecture, still open. So in other words, making sure that it works for a bunch of cases doesn't mean that then it's true. That's one of the differences between math and science. Like for example, physics, in chemistry, you say, okay, but if a enough cases, right? If enough situations this works, it seems to work, we take it for granted. Now, the good thing is that if it doesn't work at some point, then they just fix their theory, and so that now they incorporate this new case, and then we keep going with our language. You know, as long as the plane flies and doesn't fall, then we're fine. Mathematicians don't are not like that. Like if we cannot prove it, then you know you cannot formally say that it's true. Then it's still a conjecture. I don't put my hand on the fire. Okay. So, anyways, so that's why you know we cannot just say, oh, because I see that it works for up to 5, then it works for everybody. Or even if it works up to 100, then it works for everybody. No, you don't know. You have to prove it. Okay. Induction is a tool that allows you to check that this is gonna work no matter what n is. Okay. So let's try. All right. So this, if you will, this is a more formal statement. So I'm gonna call this my P of n. Okay. This is gonna be my state. My P of n, my propositional function is, you know, is in words would be the sum of the first n odd positive integers is n squared. That's the P of n that we're dealing with. In mathematical terms, is these identities that we have over here. Okay. All right. So let's prove it. So proof. So let's see. So first, so we're gonna use induction. So by induction, and the first thing that we need to do is base case. Remember. So base case. And in this case, because we are starting at 1, we want to prove that this is true for all n greater than or equal than 1. We need to make sure that it works for 1, because if it doesn't work for 1, then what are we talking about? So, in other words, we want to make sure that P of 1 is true. So in this case, P of 1 stands for the statement, the sum of all of the first 1 odd positive integer is 1 squared. The first positive integer is just 1. And indeed, 1 is equal to 1 squared. So this is true. I mean, there's nothing to do here, right? Remember, we already verified up to 5. So we know it works for 1, for 2, for 3, all the way up to 5 at least. We know it works. In particular, it works for 1. So that's true. So now, instead of keep on checking, we stop right there, and then we move to the second step, which is the inductive step, or the inductive hypothesis. I'm going to call it inductive step, but some places they call it inductive hypothesis. Okay, so what does the inductive hypothesis says? Assume that the statement works for k, and then you need to prove that it works for k plus 1, right? When you combine that with this one, you create your domino effect. It's going to work for everybody, okay? If it works for 1, it has to work for 2. Then if it works for 2, it works for 3, and so on and so forth. So inductive step, assume that P of k is true for k greater than or equal than 1, right? For some k greater than or equal than 1. This is not an empty assumption because we know it's true at least for k equals to 1. So we are safe here. I cannot say k greater than or equal than 2 until I check 2. Okay? But because we check 1, then we can say greater than or equal than 1. So assume that P of k is true for some k greater than or equal than 1. Then we want to prove that P of k plus 1 is 2. That's what we want, okay? This is what the inductive step requires. Remember, the inductive step says that you want to show that P of k implies P of k plus 1. This is what you want to show. So how do you prove this? You assume this part, and you prove this, right? That's an implication. Okay, so it's always good to write down what is it that you're assuming so that you can see it concretely, and then write down what is it that you want concretely, because this will give you an idea of what to do, okay? So I'm gonna write down here what I have, which means what we are assuming, and then down here I'm gonna write what I want, okay? So what do we have? We have that P of k is true. So P of k true means, so what does it mean? That the sum of the first odd k integers equals k squared. So 1 plus 3 plus 5 all the way up to 2k minus 1, this equals k squared. That's what we have, okay? So let's go to your formula and replace n by k, okay? That was p of k. Just replace n by k. Now, that's what we have. That's what we take for granted. We know it works at least for one, okay? Now, what do we want? We want to show that this statement with k plus 1 in it is also true. So we want the p of k plus 1 to be true as well. This we don't know. So i.e., we would like to show that if I do 1 plus 3 plus 5, all the way up to, I need to get to the next odd integer. So I'm going to write down this one, and now I need one more, right? What's the next one? What's the next odd integer? What is it? 2k plus 1, right? You need to do plus 2 to get from one odd integer to the next one. What do you do? Plus 2, right? So 2k plus 1 equals k plus 1 squared. Remember, you have to replace k by k plus 1 in the above statement, all right? So if you put a k plus 1 here, you're going to get 2k plus 1, because it's 2k plus 2 minus 1, 2k plus 1, and the k plus 1. So we have the blue, we want the red, okay? That's what we have, that's our assumption. We want to prove then that if you have the blue, you're going to have the red as well. All right? So how do we do this? This is very similar to what we did before. This is very easy now, because we have the blue, and the blue is actually very similar to the red. The only thing is that what does the red have that the blue doesn't? On the left, the 2k plus 1. So just add it to both sides. Okay? We can add it to both sides. Now the left side will be exactly what I want. We just need to do some algebra on the right and make sure to check that that will be the same as this one. Then we're done. Right? That's it. So most of these problems sometimes it's just a matter of being able to write down what you want and what you need and what you have, and then you will see what you need to do. Okay? It's just understanding what needs to be done. Okay, so now we can see what to do. We get this. We know this is equal to k squared. I'm leaving space because now what I'm going to do is I'm going to add 2k plus 1 to both sides. Okay? By adding 2k plus 1 to both sides, because we have the equality in black, now this equality holds. Everybody okay with this? I added both sides the same quantity. Now the left is exactly what I want, so that's good. We just need to work on the right. So now the right hand side is k squared plus 2k plus 1. And if you remember your little factoring techniques, you should realize, right, that this is a perfect square. Or if you want two numbers, just throw this 1 and the sum is 2. That's 1 and 1, right? So k plus 1 times k plus 1. Or in other words, k plus 1 squared. And this is exactly now what we want. That the sum from 1 all the way up to 2k plus 1 of the odd numbers equals k plus 1 squared. So p of k plus 1 is 2. You okay with this? And now you say, therefore, by the principle of mathematical induction, we abbreviate it by PMI, we have that for all n greater than or equal than 1, P of n is 2. Okay? So very good. So now this is no longer a conjecture. This now became a theorem because we just proved it. Now nobody can argue with you. Now you know that regardless of n, what do you want? The first trillion odd numbers, you know it's gonna be a trillion squared. The sum. Okay? No need to sit there and compute it. You already know. Okay. Questions? Did you understand this? All right, so let's do other examples in which we see different techniques. So the first two examples that we have done have, we have been dealing with this type of little formulas and so on. This can be done in many cases. For example, we're gonna do an inequality example now. Then we're gonna do a divisibility example. And if we have time, I'll introduce a strong induction. And we're gonna use that to do some interesting examples like this one. Just want to just want you to understand that you can use this to do many things. For example, look at this one. Given an n square rectangular chocolate bar, you know what this is, right? The chocolate bar, and they have the little square. And then you have a chocolate bar with n square. It always takes n minus 1 breaks to reduce the bar to single squares. So every time that you break the bar, you can either break it along a row or a column, okay? The question is how many times you need to break it so you have all single squares. And what we're claiming is that it will always take n minus 1 break. So if your chocolate bar has 25 little rectangles, okay, little squares, if it's a big one, then you have to break it 24 times to be able to reduce it to single pieces, okay? We'll prove that. If it has a million little squares, you need to do it a million minus 1 times, okay? And here is a more interesting one, I guess more mathematical one. It comes from geometry. You may remember this formula from high school, that if you have a polygon, okay, a convex polygon with n size, then the sum of the interior angles is n minus 2 times 480. For example, in the case of the triangle, how many sides a triangle has? 3, so n is equal to 3, it would be 1. So the result is 180, as you know. The sum of the interior angles of a triangle is 180. Well, if you have a quadrilateral with 4 sides, then it's going to be 360 because n is 4, so it's 2 times 180. If it has 5 sides, it's 3 times 180, and so on. So prove that in general. And one way to prove this is using induction. Okay, but for that we need to use strong induction. All right, so actually we don't need strong induction. We can, yes, we need strong induction. We're gonna use strong induction for that. Even though I think we can do it with regular induction. But we'll see. Once we prove it, we're gonna see if we really use strong induction or not. All right, but before we do that, let's get into the habit of using induction. So here is another example. This time it's a trivial inequality. This inequality you can prove it using calculus if you want. But you know, this here, we're gonna go ahead and we're gonna prove it using induction. Okay. So prove that n is less than 2 to the n for all positive integers n. Okay. So, and in fact, even this is even true for n equals 0, right? So I could say for all natural numbers, including 0. So just to illustrate some examples, you know, for example, when n is equal to 1, you have the 1 is less than 2 to the 1, right? When n is equal to 2, then you have the 2 is less than 2 squared, which is 4, and so on and so forth. And then what we're saying is that, you know, as you go down, the right side will just keep on getting bigger and bigger with respect to the left side. So this inequality will always hold, regardless, okay? If it's a million, 1 million is less than 2 to the million, okay? And so that's basically what we're saying. So it's a very straightforward statement. Hopefully you will believe it, but you know, it requires an argument. How can you argue this? You can argue using calculus, okay? Or even college algebra, just draw the graph and just know that the exponential is always above the line y equal x. You can think of this as y equal x and this y equals 2 to the x, and the exponential always grows on top and grows faster. So that's one way of arguing. Another way is using induction. Okay? All right, so let's do it. So proof. Remember, an inductive argument has 2 steps. The first step is always the base step. You have to make sure that this works, at least for the first value. Okay? Otherwise, you could make an empty argument and prove also all sorts of things. Okay? You need to have a base case. So by induction, we're gonna use induction. By induction n. And here, of course, P of n stands for the statement n is less than 2 to the n. Okay? So number 1, that's the base step. Basis, so base step. Basis step, and that would be for n is equal to 1. So when n is equal to 1, P of 1 stands for 1 is less than 2 to the 1. And this is clearly true. Okay? So most of the time, the basic step is just a matter of writing it down, and then you will see. in simple cases. There are many complicated situations in which you actually need to work very hard to prove your base case. And after that, then the inductive step is the one that is easy many times. All right, anyways, so this is the basic step. Now, inductive step. What do we need to do in the inductive step? It's always the same. What do we do?
Yeah.
So assume that P of K is true for some K greater than or equal than 1, because you know, you have to make sure that this assumption is valid. So we know it's valid at least for 1, okay, for K equals 1. So we need to say that. So assume it's true for some K greater than or equal than 1. Then what do we want? Then we want to prove that P of K plus 1 is also true. Okay? All right, so let's write down what we have and let's write down what we want. Okay? So what do I have? Okay, so I have that P of K is true. So that means, so what's P of K? That's a statement that K is less than 2 to the K. That's a statement for some K greater than or equal than 1. And then what do we want? We want P of K plus 1 to be true. We don't know this. So that means we're trying to figure out, is K plus 1 less than 2 to the K plus 1? This is what we're trying to figure out. And we want to prove this red inequality using the blue one. Okay? Now, inequalities, in one sense, they are more difficult than equalities, than equations, but also they are more flexible. Okay? Because in equations, you always have to make sure that you keep your equality working. For inequality, for example, you can add to both sides different things and the inequality still holds. For example, you can add a 2 here and a 3 over here, and the less than will still remain. Because if I add 2 quantities to this side, as long as I add 2 or more to the other side, I don't change the inequality. So you have more freedom. Okay? In equality, you always need to do the same thing on both sides. You either add both sides or multiply both sides the same quantity. So just understand that working with inequality is more flexible than working with equality. Okay? All you want is to preserve your inequality. All right. So let's see. So we know that K is less than 2 to the K, and with this information, we would like to get that K plus 1 is less than 2 to the K plus 1. Okay? So here is what we can do. So note, K is less than 2 to the K, right? And so if I add 1 to both sides, I get that K plus 1 is less than 2 to the K plus 1, right? Nobody can stop me from this. I just add 1 to both sides, so I immediately get that K plus 1 is less than 2 to the K plus 1, right? Now, this is not what I want. I want to have 2 to the K plus 1 on top, okay? So I would like to have here this instead of that. Now, we could do that if we show them that this quantity is less than this, then by transitivity of inequality, it will follow that this guy is less than this, right? So if this is less than this, and this is less than this, then the first one is less than the last one. That's the transitivity property of the less than. Okay, so I'm going to focus on this. I'm going to try to prove this, okay? Now, this is easy. So note that 2 to the K plus 1 equals, what is this? This is 2 to the K times 2, right? Which is 2 to the K plus 2 to the K. Everybody okay so far? Now, what do we know about K? We know that K is at least 1, so that tells me that 2 to the K is at least 2. We know that 2 to the K is an increasing function, right? So this is going to be greater than 2 to the K plus 1, since 2 to the K is greater than 1, because K is greater than or equal than 1, and the function y equals 2 to the x is increasing. Okay? In other words, if the input gets bigger, the function gets bigger. Everybody okay with this? So because K is at least 1, we know that this quantity is at least a 2, right? 2 to the k is at least a 2. So definitely this is bigger than 1. Okay? So because I have a 2 to the k here, if I replace it and I put something smaller, namely 1, what do I get? Something smaller. Okay? So that means 2 to the k plus 1 is bigger than 2 to the k plus 1. So we have the k plus 1 is less than 2 to the k plus 1, which in turn is less than 2 to the quantity k plus 1. So now if we ignore the middle guy, we get 1. Therefore, by transitivity of the less than symbol, we have that k plus 1 is less than 2 to the k plus 1. So P of k plus 1 is 2. All right. Did you understand this? So similarly, you could argue, for example, that n squared is less than 2 to the n, okay, for all n. Now, this is not always true at the beginning. This is true starting at 5. N squared is 25, and then 2 to the 5 is 32. After that, the exponential takes charge and becomes big. So try to do that one. So now you say, therefore, by the principle of mathematical induction, it follows that for all n without equal to 1, P of n is true. So we just proved that n is less than 2 to the n for all n without equal to 1. Okay? So here is as a homework for you. So prove that n squared is less than 2 to the n for all n greater than or equal than 5. Notice that up to 4, at 4 we actually, so at the beginning this is bigger. At 4 we get equality because 4 squared is the same as 2 to the 4. But then after that this guy becomes bigger. Because 5 squared is 25, 2 to the 5 is 32, and then it just keeps on getting bigger. So prove it. All right, questions? Okay, so that was that one. Then let's do another example using divisibility. So for example, let's prove that this quantity on the right. So for any n greater than or equal than 0, the number 7 to the n plus 2 plus 8 to the 2n plus 1 is always divisible by 57. So it's always a multiple of 57. Okay. So remember, this means so I 7 to the n plus 2 plus 8 to the 2n plus 1 is a multiple of 57, which means in terms that it can be written, all of these things are equivalent things. This equals to 57 times some integer k for some integer k. Okay? That's what it means when you say that 57 divides this number. So we want to show that regardless of what n is, this quantity that you get on the right is always 57 times something. Okay? All right. Do you understand the statement? All right. So now let's prove it. Okay. So to prove this, we're going to use induction. So proof by induction. And then, of course, when you want to use induction, you need to have a statement. What's the statement that we want to show? So what is our P of n? Our P of n is the statement that 57 divides that quantity. I'm going to write it this way because it's more comfortable to work with. Okay, to have this way. Our P of n is that 7 to the n plus 2 plus 8 to the 2n plus 1 equals 57 times k for some integer k. Okay, let me call it m because we're going to use k for our inductive thing, and then make sure that we don't use the same letter in two different contexts. So P of n stands for this. 7 to the n plus 2 plus 8 to the 2n plus 1 equals 57 times n. for an integer n. Okay, so that's my P of n. Notice that this is your proposition of n. All right, so what's the first step? So basis, right? Basis step. So what's our basis step according to the problem? What is it? Are you sure? Look at the problem. What does it say here? For all n, we want to show that this works for all n greater than or equal than 0. So what's our base case? N equals 0, right? So base step is P of 0. Do you understand this? Okay, so P of 0. So let's write it down and let's see if it's true or not, right? So P of 0 stands for the statement 7 to the 0 plus 2 plus a to the 2 times 0 plus 1 equals 57 times n. Let's see if it's true. In other words, is this a multiple of 57? Well, let's see. Oh, nope. 7 to the 0 plus 2 plus 8 to the 2 times 0 plus 1. This is just 7 squared plus 8, which is 49 plus a, which is 57, which is 57 times 1, right? So indeed, this is true because we found that this expression equals 57 times an integer, namely times 1. Okay, it equals 57. So P of 0 is true. You okay with this? All right. So it works for 0. Now we want to show that it works for 1, it works for 2, for 3, for 4, and everybody else. So instead of doing that case by case, we just go now straight to the inductive hypothesis. Suppose it works for k, let's prove that it works for k plus 1. Okay? So, inductive step, assume P of k is true for k greater than or equal than 0, for some k greater than or equal than 0. Okay? So, we want to show that P of k plus 1 is also true. Okay? All right. Again, this is not strictly necessary what I'm about to write, but it's always helpful. So it's always, once you write this sentence, this line, you always need to write something like this. You need to state what you are doing. Okay? You need to tell me what you're doing. So you're assuming k, and then you want to prove k plus 1. Okay. It's always now good to write down what is it that you have completely. So, I've been writing every single time. So I'm gonna write what I have, and then I'm gonna write what I want. And hopefully this is gonna spark some ideas. So let's see, what do we have? We have that P of k is true, so I'm just gonna write directly what I have. So that means I have that if I do 7 to the k plus 2 plus a to the 2k plus 1, I know I can write this as 57 times some integer. I'm gonna call it m1, okay? For some integer m1. Everybody okay with this? It's what we're assuming when you say that the statement is true for k. Now, what do we want? We want to show that the statement is true for k plus 1. Let's see, who can tell me what should I write here? How does the statement look like for k plus 1? What should I write? What do I write? 7. What else? Say it. Don't be afraid. If it's wrong, it's wrong. What do I write?
2k plus 3.
So, okay, in the 7, why 2k? Where is the 2k coming from?
Because k plus 2 plus k plus 1.
No, so you want the statement for k plus 1. So that means whenever you see a k, you replace it by k plus 1. So what is it? K plus 3. 7 to the k plus 3 plus, what do I write now? What is it? 2k plus 3. Very good. equals 57 times something. I'm gonna call it M2. Again, all you have to do is replace K by K plus 1. Okay? So you put a K plus 1 here, you get K plus 3. You put K plus 1 here, you get 2K plus 2 plus 1, that's 2K plus 3. Have to be careful. If you get confused with that, then you're gonna get the problem wrong. Okay? So you have to make sure that you understand what is it that you need to prove. So I want to prove that this quantity equals 57 times some integer. And what do we have to work with? Well, what we have is what is in blue. Okay? We know what's in blue. With that, somehow, we want to end up what is in red. Now, here there are many ways to deal with this type of problems. Okay? You could begin with the blue and then start to manipulate that. Since we already wrote down what we wanted, that's why it's helpful to write down what you want so you have something visual. You can start to do algebraic manipulations to your blue expression to build your red expression. Okay? Alternatively, what you could do is you could start with the red, the left part at least. Nobody can stop you from writing this. It's just that you don't know if it's 57 times something. You can write this. And then start doing something to this as a series of equality until eventually the blue somehow comes into play, and then you can end up with this. I think that's harder to do. Okay? It's easier to start with the full blue equation, and then guided by what you want, you start doing manipulations to it. You will see what I mean. Okay? It's way easier to do it that way. So, at least in my opinion. So let's try. Okay, so what do I have? I have that 7 to the k plus 2 plus 8 to the 2k plus 1 is equal to 57 times m1. We know this is our assumption. Now, what I want to do is from here, I want to somehow deduce the red. So here's what I'm going to do. First of all, I'm going to try to build my left-hand side. I want this left-hand side to match as much as possible the left-hand side over here. So the first thing that I notice is that I have a k plus 3 in the power of 7, and I don't have it here. Yes? How can we fix that? How can I make this power to be k plus 3? What am I missing to get a k plus 3 here? 1. How can you get a plus 1 in here? Property of exponents. How can you do a plus 1 here? Multiply by 7. So the first thing I'm going to do is I'm going to multiply this equation by 7. Why? Because then I'm going to do 7 times this guy, and it's going to bump up the power 1, and I'm going to have my 7 to the k plus 3 at least. Do you understand this? That's the first thing that I'll do. So first thing is I'm going to multiply everything by 7. Now, this is not a random thing. I'm doing it motivated because I want a k plus 3 here. And if I want that, then I need to multiply by 7. Okay? All right. So multiplying by 7, what do I get? I get 7 to the k plus 3 plus 7 times 8 to the 2k plus 1 equals 57 times 7m1. I don't want to multiply, I want to stress the fact that I still have a multiple of 57. Remember, our job is to show that this is a multiple of 57, so I want that 57 there. I'm not going to multiply. I'm just going to leave it there. Okay. Okay, good. I have my 7 to the k plus 3, but still, there's something that needs to be done here. So now it's time to somehow work in here. Now here is the tricky part. I need to work here without affecting this guy. Because if I affect this, then I'm changing what I have, right? I would like to do something here without touching this. Do you understand this? All right. So again, same idea. What am I missing? What do I want to have here in the power of 8? So I need 2 extra 8s, right? So I will have a plus 3 instead of a plus 1. So that means I will somehow need to multiply this by a squared. Yes? Now, you cannot just multiply both sides by a squared, because then that's going to come in here, and then we're not doing anything, right? So how can I get an a squared from here? So this is the tricky part, but once I show it to you, then now you know it. Okay? There's a 7 here. So a squared is 64, right? Now, can I write this 7 as 64 minus something? Right? I mean, nobody can stop me by modifying this 7. I could rewrite this 7 as 64 minus what? 57. That's why this thing is a multiple of 57, because we can do this thing, right? It turns out that if you do 64 minus 57, you get 7. Now you can find this easy, right? Just do 64 minus 7 to get the 57, okay? So that's 7. I will rewrite it as 64 minus 57. Why? I mean, I'm telling you why. So now, why is this helpful? Well, because now we can distribute, right? We have our 64 that we wanted, so this is going to bump up to 2k plus 3. But then the other piece is what? It's a multiple of 57 that we can move it to the other side, factor the 57, and then we're done. Okay? So this is now 7 to the k plus 3 plus, I distribute the 8, so 64 times 8 to the 2k plus 1, that becomes 8 to the 2k plus 3. Everybody okay with this? 64 is a squared, okay? But then you have minus 57 times this is the leftover part. But that's not a problem because this leftover part is a multiple of 57. I just move it to the other side, factor by 57, and I get my multiple. So 7 to the k plus 3 plus 8 to the 2k plus 3 is going to be equal to 57. I'm going to factor it already, okay? So I have 7m1 plus 8 to the 2k plus 1. So I move this guy to the right positive, and then I factor the 57. Are you okay with this? If you distribute this, you get exactly this plus this one. Everybody okay with this? All right, now, what is this parenthesis? What type of value is this? It is an integer, a fraction, a real number. What is this? This is an integer. Why? Because m1 is an integer and k is an integer, so it's an integer. So that's your m2. Okay, so you can call that your m2 right there. So we just show that this quantity equals 57 times something. So this is an integer since m1 and k, they're both integers. Okay? So that means that p of k plus 1 is 2. Okay? All right. Questions? Did you understand how one line led to the next one? So all of these problems, you can do it like that. It's essentially the same idea. So start with what you have, then modify the first one by multiplying by an according quantity, whatever it is, okay? Once you have that one fixed, now you will have that thing that you multiply, you will have it here for the second term. Well, break that one down into what you need. What do you need? I need a 64 so that I get a plus 2 in here. Okay, I write 7 and 64 minus something. It turns out that that's something, if the problem is going to work out, that something has to be a multiple of what you want. Because if it's something else, then there's no way for you to get the 57. That's why we said 57 and we didn't say 56 or 53 or something else. Okay? So that's one technique. If you want, think about how to do it the other way. Starting with this and then building, trying to come with the blue. It can be done also nicely because here you can get the k plus 2 by taking out a 7, and here you can get the 2k plus 1 by taking out an a squared, the 64. It's essentially the same thing, it's just like doing it backwards. Then the 64, you are going to split it as 64 minus 7. Why? Because there was a 7 here that you can factor to get that expression popping up. But I think it's easier this way. So that's why I'm just playing this way. Okay, so this is more or less how these divisibility questions go. Any questions? Okay.